This video will look at linear Diophantine equations. Particularly, we will determine when a solution exists, and if a solution does exist, we will use that solution to parameterize all solutions and then give three more solutions from that parameterization. So these are the examples we are going to look at. As a reminder, here is our theorem about these type of linear Diophantine equations. The linear Diophantine equation ax plus by equals c is going to have a solution if and only if d divides c, where d is the GCD of a and b. So if we do have a solution, say x0, x0, y0, then all other solutions can be found by this parameterization, where we let x be x0 plus b over d times t, and y is y0 minus a over d times t. Let's look at our first example. 195x minus 221y equals 65. Before we go too far, let's see if this will have a solution by checking that first. So check to see if it has a solution. Okay, the way we check to see if the solution exists is we need to find the GCD of 195 and 221 and check, does it divide 65? Okay, so the first thing we need to do is find that GCD. I have already done this work for us. And here we go. And we can see that the GCD of 221 and 195 is 13. So what we're asking, does 13 divide 65? And the answer is yes, because 13 times 5 is 65. So this linear Diophantine equation will have a solution. So what we're going to do is find a solution and then use that to generate some more solutions. Okay. We've already done actually step one of finding the solution. Step one is to use this Euclidean algorithm to find the GCD. And now I will take this algorithm and write my GCD 13 as a linear combination of 195 and 221. And what that will do is allow me to then generalize to more solutions. So let's do the rest of this. I've actually already done the work to save us some time. So let me find where I've done it. Here we go. So when we do our linear combination of 195 and 221, we get this. So think about what this is telling us. This is saying that 13 is 8 times 195 minus 7 times 221. But notice what we want to do is look back to our original. We want to figure out some solutions, but we want it to equal 65. So I'm going to multiply my entire equation by 5. And notice now I'll have that 65 equals, well, 5 times 8 times 195 minus 7 times 225. So 65 equals 40 times 195 minus 35 times 225. 221. Excuse me, I've been writing the wrong number. Let's go back and erase those mistakes. 221 was my other number, so 221, 221. There we go. I think I've corrected my mistakes there. So what does that tell me? If I look back to my original, it looks like 195 times x, 195 times 40. So I have x is 40. And then minus 221y. So minus 221, that tells me that y must be 35. Equals the 65 I was looking for. So there is a solution. X equals 40, y equals 35. And you can quickly spot check or quickly check to see if you're correct. Plug your solution back into your original and make sure it comes out correctly. All right, so the next thing we want to do is parameterize our solutions using this solution. So the way we'll do that, let's kind of come to the other side over here. We will use the equations from before, so let's back up for just a second and remind ourselves what those were. So looking here in the middle, your x is x naught plus b over d times t, and your y is your y naught minus a over d times t. So let's write that down. X is x naught plus, make sure we write all this down, b over d times t. And your y is y naught minus a over d times t. And this is where you are looking at ax plus by equals c, and d is the GCD, okay, of, I guess, a and b. We'll write that down too. Okay, so let's clean this up. So x is x naught, well, that's 40. That was our original. Plus b over d, that'll be negative 221 over 13 times t. And then y is, our y value was 35 minus 195 over 13 times t. And cleaning these up, we get x equals 40 minus 17t, and y equals 35 minus 15t. So this is our set of parametric equations that will describe all solutions. Notice if you let t equal 0, it just goes back to your original x equals 40 and y equals 35. But we can find other solutions by letting t be anything we want. So other solutions. Again, we can let t be anything we want. I'm going to let t equal 1 because that's easy to plug in. If t equals 1, then x is 40 minus 17 times 1, which is 23. And y equals 35 minus 15 times 1, which is 20. So there's another solution that we've generated. You could quickly plug that back into the original to see if it's correct. We could let t equal 2. Again, t can be anything because this is a set of parametric equations. So we do want to restrict it to integers because we're only interested in integer solutions. But, oh, actually, no, that doesn't matter. No, yeah, we want to restrict it to integers or things that right here would make integer solutions. So yeah, I would just use integers because otherwise you're going to want to cancel out a 17 and a 15 and make your fractions go away. So these are integers. So I would stick to integers just to make life easier. We can let t equal 2. We get x equals 40 minus 17 times 2, which is what, 6? And y is 35 minus 17 times 2. Sorry, not 17. 15. Sorry, I was copying y down incorrectly. 15 times 2, which that ends up being a 5. And, you know, t can be whatever, so I'm just for the last one, I'm just going to let it be negative 3 just to do something different. Here, x would be, what, 40 minus 17 times negative 3, which ends up being a 91. And y could be, then would be 35 minus 15 times negative 3, which ends up being an 80. So what I found over here is 3 more solutions of my original. Okay. All right. So let's do another one. We have 172x minus 88y equals 102. So again, I'm going to start by finding the GCD here because I want to check does the GCD of 172 and 88, does it divide 102? Oops, just writing my question mark already. 102. So there's my question. That's what I'm trying to figure out. So I've already done the GCD work using the Euclidean algorithm. So let's plug that in. Here we go. So here is where I have done it. Turns out that the GCD is 4. So this is saying, does 4 divide 102? And the answer is no. So there is no integer solution here to this. All right. Let's look at our next one. 246x minus 312y equals 270. So again, we want to check, does the GCD of 246 and 312, does that divide 270? That's our question. Again, I've already done the GCD work for us, so let's pull that up. Got to find where I did it. There we go. Oh, that's big. Make it a little bit smaller. All right, so it turns out that 6 is the GCD of these two numbers. So I guess what we're saying, does 6 divide 270? And it turns out that yes, 6 does divide 270. So we are good to go. We will be able to find a solution. So how did we find that solution? Well, we rewrote 6. We need to rewrite that GCD 6 as a linear combination of 246 and 312. Remember, that's when we go backwards through that Euclidean algorithm. I have already done that work as well. So if you want to pause here and try to do it yourself just to make sure you can, or here we go. Here is the work. If you go backwards through that algorithm to get that linear combination. So it looks like it's telling me that 6, which is that GCD, is 15 times 312 minus 19 times 246. I'm reading that from that last line. But I don't want 6 to be a linear combination of 246 and 312. I would like for 270 to be, which means I need to multiply everything by 45 so I can get to that 270. So 270 equals, I'm going to multiply by 45. When I do that, I get 675 times 312 minus 855 times 246. Okay. So what does that tell me about my values of x and y? So let's look up here. My x is what's with my 246. So it looks like x is negative 855. And my y, I look back at that, y is, well, I guess negative y is with 312, so I need to worry about my opposites here. It's going to be negative 675. Okay. And again, you could quickly check that by plugging those into the original and making sure that it does equal 270. So there's one solution. From this one solution, we want to generate more. So again, we'll parameterize these. Okay. So if we go back just a couple, I'm just going to copy paste this here so we have it. Let's copy this. Oop, I copied more than I wanted. Let's copy this and then put it over here. So we have that as our reference to find these parameterizations. So what are we going to get? X equals, well, our x value that we found as part of a solution is negative 855 plus, and one thing you can kind of do to keep up with these a little bit better. So the x value, negative 855, the b is always what with the y. So I see the negative 855, so I'm going to use the 312 with the x part. So 312, or negative 312 was a negative, wasn't it? Negative 312 over my GCD, which was a 6, times t, and then y will equal negative 675 minus 246 over 6t, and we can clean these up. X is negative 855 minus 52t, and y is negative 675 minus 41t. So this, what I found here, is my parameterization. So for plug in any values of t, I can find a solution. Again, I can use whatever values of t, but usually we use, nice small values just to make life a little bit easier. So other solutions. So we have t equals 1. We can use that. We have x equals negative 855 minus 52 times 1, and that gives us negative 907. and we have y equals negative 675 minus 41 times 1, and that's negative 716. So there's one solution if we let t equals 1. Maybe we let t equal negative 2. Remember, just let it equal some integer, and you'll be sure to get an integer as your solution. So we got x equals negative 855 minus 52 times negative 2, which is negative 751, and y equals negative 675 minus 41 times the negative 2, and that ends up being negative 593. And just for kicks, let's maybe just say let t equal negative 10, just something a little different. X would be negative 855 minus 52 times negative 10. That ends up being negative 335. And y equals negative 675 minus 41 times the negative 10. And this ends up being negative 265. And there we go. We have found 3 more solutions to this linear Diophantine equation.